Exams are near. But why fear when Tech Explained Story is here? Hello, everyone. I am your Tech Explained Story, and I've come with a detailed one-shot of a crucial chapter. Exams are approaching, and fear is natural. But today, we'll tackle that fear head-on. We're diving into magnetic effects of electric current, a seemingly small chapter that often yields very tough questions in board exams. This one-shot will cover every possible question and topic in detail over the next 1.5 hours in our fun, engaging style. What is a magnet? A magnet is an object that attracts materials made of iron, nickel, and cobalt. It produces a region around it where its magnetic force can be felt. Magnets have two poles, north and south. Like poles repel, opposite poles attract. A freely suspended bar magnet always aligns itself in the north-south direction. A magnetic compass is a small magnet, a needle that uses this property to show direction. Magnetic field and field lines. The region around a magnet where its force can be detected is the magnetic field. We represent this field using imaginary magnetic field lines. Key properties: they form continuous, closed corvies. Outside the magnet, they emerge from the North Pole and enter the South Pole. Inside the magnet, they run from the South Pole to the North Pole. The closeness density of the lines indicates the strength of the magnetic field. Closer lines mean a stronger field. Field lines never intersect each other. If they did, a compass placed at the intersection would point in two directions simultaneously, which is impossible. Oersted's experiment. Hans Christian Oersted discovered that an electric current creates a magnetic field. In his experiment, a compass needle deflected when placed near a current-carrying wire. Changing the current's magnitude, change the deflection, and reversing the current reversed the deflection's direction. This proved that a current-carrying conductor produces a magnetic field around it. Right-hand thumb rule. Maxwell's rule. This rule determines the direction of the magnetic field around a straight current-carrying conductor. Rule. Imagine holding the conductor in your right hand with the thumb stretched out. If the thumb points in the direction of the current, the curled fingers show the direction of the magnetic field lines, concentric circles around the wire. Convention. A dot represents current magnetic field coming out of the page. A cross X represents current magnetic field going into the page. Magnetic field due to a current-carrying circular loop. For a single circular loop, the magnetic field lines are circular near the wire. However, at the center of the loop, all these fields add up to create a straight, uniform magnetic field. Solenoid. A solenoid is a long coil of many insulated copper wire turns shaped like a cylinder. When current passeth through it, it produces a strong, uniform magnetic field inside it, parallel lines. The magnetic field pattern outside resembles that of a bar magnet, with clear north and south poles. Its strength depends on I, number of turns per unit length. The strength of the current. 3, nature of the core material. If freely suspended, it aligns in the north-south direction. Its polarity can be reversed by reversing the current direction electromagnet. When a soft iron core is placed inside a current-carrying solenoid, it becomes an electromagnet. Its advantages over a permanent magnet are: its magnetic strength can be controlled by changing current. Its magnetism is temporary, disappears when current stops. Its polarity can be reversed. It is used in electric bells, cranes, motors, and laboratory equipment. Force on a current-carrying conductor in a magnetic field. Oersted showed a current creates a magnetic field. Conversely, a magnet exerts a force on a current-carrying conductor placed in its field. This is the principle behind electric motors. Fleming's left-hand rule. This rule determines the direction of force on a current-carrying conductor in a magnetic field. Rule: stretch the thumb, forefinger, and middle finger of your left hand mutually perpendicular. Forefinger points in the direction of the magnetic field. Middle finger points in the direction of the current. Thumb points in the direction of force motion. Memory aid: father thumb, force, mother forefinger, magnetic field, child middle finger, current. Factors affecting this force. The force is maximum when the conductor is perpendicular to the magnetic field. Nonagésimo. It is 0 when the conductor is parallel to the field. 0 or 180. Domestic electric circuits. Houses receive an AC electric supply of 220V. Appliances are connected in parallel so that each gets the same voltage, can operate independently. And devices of different power ratings can be used. Live wire red. Carries current from the power station at high potential 220 volts, dangerous to touch. Neutral wire black. Completes the circuit by returning current to the power station at zero potential. Safer to touch. Earth wire green. A safety wire connected to a deep underground metal plate. It provides a low resistance path for a leakage current, preventing electric shocks by directing it into the ground. Safety devices. Fuse. A safety device with a wire of low melting point and high resistance. It is always connected in series with the live wire. During overloading or short circuit, excess current heats and melts the fuse wire, breaking the circuit and protecting appliances. Circuit breaker, MCB, an automatic switch that turns off during overloading or short circuit. Short circuit versus overloading. Short circuit occurs when the live and neutral wires accidentally touch. Resistance becomes nearly zero, causing an extremely high current, leading to heating, sparks, and fires. Overloading occurs when too many appliances are connected to a single socket, drawing current beyond the circuit's safe capacity, causing heating. AC versus DC. AC alternating current. Current that reverses direction periodically, for example. Household supply 220 volts, 50 gigs. Efficient for long distance transmission. DC. Direct current. Current that flows in one direction only. For example, batteries. Cannot be transmitted efficiently over long distances. Conclusion. Remember, this phase of your life is precious. Work hard with belief in yourself. You have the ability to make yourself and your parents proud. Keep going, manage the pressure, and enjoy the journey. All the best for your exams. Logo image suggestion. A stylized, friendly cartoon figure. Tech explains story holding a magnet in one hand and an electric wire with a spark in the other, smiling confidently. In the background, simple icons of a bar magnet, a solenoid, and a house with wiring. Text. Tech explains story. Science made easy.